introduce the torque, and together with the rotational inertia, we have those important quantity to describe the rotational motion. And the key information for us is that the rotational motion can also be controlled, described by the Newton's second law for rotation, which is torque equals to I alpha. I is the rotational inertia, alpha is the rotational acceleration or the angular acceleration. This one can be compared with F net equals to F A. Okay. Now, let's look at this problem. We have a block of mass, small m, passed from a string wrapped around the frictionless disc-shaped pulley of mass capital M and the radius r. The block descends from rest under the influence of the gravity. What is the magnitude of the linear acceleration? Okay, first let's think about this one. We have the problem with pulley before, but usually we don't consider the mass of the pulley. If this is a very light pulley, so the mass can be set at 0. So it wouldn't affect the motion of the block. The only effect of the pulley is to redirect the tension, right? For example, you have this problem before. So in that case, you consider the mass of this one, mass of this one, but you don't consider the mass of the pulley. But now, so for example, if I attach a block to a massless pulley, then what kind of motion for this block? If the pulley is massless, so what kind of motion for the block here? Free falling, right? Okay, because you don't have the mass for the pulley, so it's just like a free falling. You have a string attached here, but it will rotate nothing. But now, so in that case, you know the acceleration will be 9.8 meter per second squared. But now, if you have some mass for the pulley, so when this block is dropping, it will also rotate the block. So then you can expect the acceleration in this case should be smaller than 9.8. Okay. Because it has to rotate the block. It will take off some of your efforts to drop it. Okay. So in this case, we have to calculate the acceleration, the linear acceleration of the block. So that's what happens to here. So you can see how can we calculate this problem. The mass of the block, the pulley is capital M. The mass of the block is small m. Okay. Here you have the radius r. Now, we want to find the acceleration of the block. So anyway, that means we have to do the force analysis for the block. Okay. So we get mg and tension T, right? Okay. So we need somehow find out the tension T to calculate the acceleration of the block. So we have some acceleration K here. On the other hand, the pulley is undergo a rotation. So if this one has some acceleration A, this one must have some angular acceleration alpha. Okay? And if you analyze the motion of the pulley, so there are some forces acted on the pulley, and it will produce, they will together will produce some torque to rotate it. Okay. So let's see how many forces acted on this pulley. Okay, can you tell me how many forces do you have in total?
Tension?
Okay, you have the tension T for this one, right? Anything else? Okay, itself has some gravity acting on the center, capital Mg. Anything else?
Does it have a normal force from where it's attached?
At the center, you should have some normal force to support it, right? Okay. So for this pulley, you have three forces: T, gravitational force, and the normal force. So the equation we are going to use is that this one, linear motion. So we are going to use F net equals to ma. Okay. For the pulley, it's under rotation, so you need to use I net for the top net. Okay. This is torque net. So you have to use the net torque equals to I alpha. Okay? Now for this one, this is easy. You can expand this one. You have two forces mg, tension. So the Newton's second law for this one is actually mg minus t equals to ma. Right? Okay. So our main issue is to write this out. Okay, the rotation of Newton's second law. Let's look at if you want to calculate the net torque. In principle, the net torque is the torque produced by the tension, the torque produced by the normal force, the torque produced by the gravitational force. So together you get some torque T plus torque N plus torque, let's call it torque G. Okay. Together will give you I alpha. Now here, can you tell me what is torque N? The torque produced by the normal force N. Okay, in fact, if you think about the definition of the torque, you can easily give me the number. You don't have to do any calculation. What's that? Okay, how do you know it's zero? Okay, if you look at the general case, if something is in rotation, okay, the torque is the force multiplied by, okay, the R perpendicular multiplied by the force, right? So for example, in this one, this is R perpendicular. For like this one, this is R perpendicular. Okay. Now, think about this case. If the force goes through the center of the rotation, how can you draw the R perpendicular? So you want to find the R perpendicular. By definition, it's the distance from the center to the straight line of the force. In this case, what is the distance from the center to the straight line of the force? 0, right? So this is a very important special case. If the force goes through the rotational center, then the torque produced by the force will be 0. That's reasonable, right? If you want to rotate the object and you act a force on the center, it wouldn't produce any rotation. Okay. So the normal force goes through the center, so the torque is 0. Similarly, what's called G? 0. Okay, because also the gravitational force goes through the center. So the two forces will not produce torque. Okay? You only need to look at those forces which is not goes through the center. So you have the torque produced by the tension. And again, if you want to calculate the torque produced by the tension, it should be R perpendicular multiplied by the tension force. So R perpendicular multiplied by T. Okay. equals to here I. How can we calculate the rotational inertia for this object? Okay, we mentioned this is a disc-shaped pulley. And for disc, what is the rotational inertia? Do you remember? 1/2 mr squared. So capital M and R is given. So this is actually given. Multiple alpha. Okay? Now, another thing. So here, but we still need to identify R perpendicular and alpha. Okay? For R perpendicular, in this case, can you see that R perpendicular will be exactly the same as R, right? Because, and here if you draw this is R, and if you draw the R perpendicular, it will be the same straight line, same distance. Because the tension, of course, perpendicular to the line here, right? So in this case, you get, this equation becomes RT equals to 1/2 mr squared multiplied by alpha. Alpha is the angular acceleration. So how does the angular acceleration alpha is related to the linear or the tangential acceleration A? Remember that? Okay, what is the relationship between alpha and A? The acceleration equals to alpha multiplied by R, right? So alpha equals to A divided by R. Okay, so this is an important relationship here. So alpha equals to A divided by R. So now you can see many of the quantities here can be cancelled. This R cancel one of the R here. And this R also cancel one of the R here. Right? So this equation actually, finally you get two equations. One is this. Another is from here T equals to 1/2 mA. Now you want to solve for A. After all this is quite straightforward. You can just substitute T here. Then you get mg minus 1/2 capital MA equals to MA, right? And then you will get A equals to mg divided by M plus capital M over 2. That could be your answer. Okay? Any question here? Okay. So you can see here, formally, we still have the Newton's second law. Looks very similar to the linear Newton's second law. But you need to remember many of the conceptual definition here, right? How can you handle the torque? Some of them were very easy. Some of them are related to the R. Okay, and how can you calculate rotational inertia I? And how can you calculate the linear, the rotational acceleration alpha? Okay, all these quantities you need to understand them conceptually, so you can write down the definition. Any question here? Now,
on the 1/2 M1 squared over A over R, how do you get the R on the bottom of the A?
this one? Alpha equals to A over R. Okay? Remember that there is a relationship between all the linear quantity and the rotational quantity, right? So we have linear quantity S, V for the rotation, and A, right? Arc length covered by the motion, the tangential velocity V, and the tangential acceleration A, and we have theta, omega, and alpha. Angular displacement, angular velocity, angular acceleration. There is some relationship between them, right? So this is, you have to be familiar with. This equals to this one, this equals to this one, this equals